Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be working on Unit number 10, Lesson number 2, on the graphs and zeros of a polynomial. In the last lesson, we looked at power functions, and we even examined a little bit about how the end behavior of polynomials relates to the end behavior of the power functions. Today, we're going to incorporate that together along with the zeros of a polynomial to really start to understand about how graphs of polynomials behave. But first, let's make sure that we review the definition of a polynomial. All right. Polynomials are functions that have the following form. Now, this can look awfully confusing, so let's try to kind of understand this, right? Polynomials look like y equals a coefficient times x to a whole number power plus another coefficient times x to a whole number power that's one less than the previous one. And we're going to keep doing that all the way down until we have an x to the first and then a constant term. So for instance, your classic parabola, y equals 4x squared minus 3x to the first plus 1, notice, 1 less, right, is a polynomial. We don't have to have all the powers there. For instance, here, y equals 1/2 x to the fifth minus 2x squared plus 1, that is certainly a polynomial as well. One could kind of claim that there are the other terms, like 0 times x to the fourth plus 0 times x to the third. All right, we don't have to have them all there, but the key is, right, those powers have to be whole number integers, positive integers. This is another good example. Y equals 6x cubed minus x to the first. That's a good example of a polynomial. All right. On the other hand, y equals x to the 1/2, that is most certainly not a polynomial because the 1/2 is a fractional power. All of those powers have to be positive exponents. Likewise, y equals x to the minus 2 also can't be included in a polynomial. No negative exponents on the variables, all right? So polynomials are collections of power functions, This thing is a power function, right? But the powers have to be positive numbers. And we can also have constants thrown in at the end, all right? Polynomials are extremely important, and you played around with them a little bit in Algebra 1. But we're really going to be investigating them quite a bit in this lesson and the next lesson. So let's jump into it and start to play around a little bit with a cubic polynomial. I think we've had enough with quadratics, right? We've graphed parabolas to no end. But let's take a look at some cubics, okay? The thing about quadratics, ones where the highest power is x to the second, is that, they all pretty much look the same. But what we're going to do here is graph 3 different cubics in the same window and see how their x-intercepts, right, also known as their zeros, differ. All right, so what I'd like you to do is I'd like you to take out your graphing calculator and I'd like you to graph each one of these things, but I would graph them separately and sketch the graph and also circle their x-intercepts. I'm not going to bring out our TI-84 right now because you've certainly seen how to graph many, many times. So I think you can do that on your own. But pause the video now and graph each one of these 3, and then I'll sketch the graph that you should have come up with. All right. Well, the first one, the graph roughly looks something like this. All right, and it has 1, 2, 3 zeros. And notice its ends are pointing in the opposite direction. Remember that from the last time? Right, because its long-run behavior is dictated by that term, y equals x cubed. So they point in opposite directions. But there are 3 zeros. On the other hand, letter B, right, 2 turning points, but only 1 0. Again, notice the ends pointing in opposite directions. And letter C, we managed to get one. Now, this was probably the trickiest of them all, that had exactly 2 zeros, because one of those two zeros was tangent to the x-axis. So we had 3 zeros, 1 0, and 2 zeros. All right? And that's not a coincidence that we could have up to 3 zeros. Just like a parabola can have 2 zeros, a cubic can have up to 3. It can't have 4 though. All right? And we're going to be investigating that for the rest of this lesson and in the next lesson. But take a look at that, get a feel for it, and also keep in mind that end behavior pointing in opposite directions because we have a cubic. Pause the video now. All right, let's clear out this text. All right, in exercise number 2, it says consider the cubic whose equation is x cubed minus x squared minus 12x. All right. Letter A says algebraically determine the zeros of this function. Well, in order to find the zeros of any function, what we're going to do is we're going to set that equation equal to 0. Now, how can we solve that equation? Well, we can't use the quadratic formula because the quadratic formula only works with ones where the highest power is x to the second. But we can use the zero product law if we can factor this thing. And the great thing is that we can factor it. We can completely factor it. Notice that for each one of these, there is a common factor of x. So if I factor that out, right, then I have this equation. Now, I don't want to lose that x right there, but I can now factor that trinomial using a little guess and check, right? X and minus 4, positive 3. Now, before we go on, I really want you to step back and look at that. Okay, that is the factored form of that cubic. And now the zero product law makes it very easy, right? I can set this thing equal to 0. I can set this equal to 0. And I can set this one equal to 0. And so I find 3 zeros or x-intercepts. One at negative 3, one at 0, and one at 4. Now, believe it or not, that should actually be enough to create a relatively good sketch of this. Now, why is that? Even without our calculator, we know that the end behavior of this polynomial should look like y equals x cubed. And if you remember from our work with power functions, y equals x cubed has tails that point in the opposite direction. It kind of looks like this. So this cubic will end up looking like this. All right. Now what I'd like you to do for a moment is I'd like you to pause the video, put that cubic into your calculator, and verify that that's the way it looks. Okay, pause the video now and give that a try. All right, isn't that kind of cool? If we know the zeros of the polynomial, right, and of course we know what kind it is it a cubic, is it a quartic, that's x to the 4th, etc., then we'll know which way that the ends point, and we can actually understand what that polynomial looks like without ever having to use our graphing calculator. We only used it there to verify, not to get our final answer. Pause the video now and write down anything you need to. All right, let's clear that out and go on to the back side of the sheet. All right, now I'm glad that we have our calculators out because let's take a look at this one. It says exercise 3. The largest root of x cubed minus 9x squared plus 12x plus 22 equals 0 falls between what two consecutive integers? All right, now consecutive integers, right, are things like 4 and 5, 6 and 7, 10 and 11, 8 and 9, right? Consecutive integers. So what I'd like you to do is pause the video now and see if you can use your calculator to solve this problem. All right. Well, the key here is to graph this cubic on your calculator. And if you do that, you may have to play around with the window. But eventually what you end up having is you end up having a cubic that looks something like this. All right. Now the largest zero is over here. And what we end up finding is that that crosses the x-axis between 6 and 7 for choice 2, right? And again, the key here is understanding the link between this equation and the zeros of this cubic function, right? Wherever the zeros of this function are the solutions of that equation. Very, very important to understand that. All right? Pause the video now and write down anything you need to. Okay, let's clear this out and work with a quartic and x to the fourth. Now, obviously, well, it may not be obvious, but as the powers get higher, right, to me, the behavior of the polynomial gets more interesting. So just like before, this problem challenges us in letter A to algebraically determine the x-intercepts of this function. So what I'd like you to do is pause the video right now and make an attempt at this. Try to algebraically determine the x-intercepts of this function, or the zeros, right? The x-intercepts, the zeros, the roots, all the same thing. The zeros of the function. You know, try to find those, okay? Pause the video now. Okay, well, let's do it. We have x to the fourth minus 5x squared plus 4 equals 0. Well, again, can't use the quadratic formula, or could we? Anyway, let's just pretend we can't use the quadratic formula. There is a way to do it. We have to factor this. Now, this thing would have to be an x squared times x squared to give me an x to the fourth. But then we can have a minus 4 and a minus 1, right? And that gives me negative 4x squared and negative 1x squared, and those would combine to be that negative 5x squared. But then we can factor the x squared minus 4 into x minus 2, x plus 2, and the x squared minus 1 into x minus 1, x plus 1. And then this would give us x equals 2. This would give us x equals negative 2. This would give us x equals 1. And this would give us, x equals negative 1. Wow. 4 x-intercepts, one at negative 2, one at negative 1, one at positive 1, and one at positive 2. B says verify your answer to part A by sketching a graph of the function on the axes below. Now it says verify it. So what I'd like you to do is actually take your graphing calculator out and set the window up according to those axes and take a look at what this quartic looks like. All right, and it looks really neat. It's a nice even quartic. Not all quartics are even, but this one it's got that nice symmetry across the y-axis, no matter how well I've drawn it, and it looks something like that, right? Nice even quartic. And notice how the ends point in the same direction because, again, the end behavior of this polynomial is dictated by y equals x to the fourth. Now, it looks very different than y equals x to the fourth. Y equals x to the fourth kind of looks like this. And it doesn't have all those crazy cool turning points. Those are caused by the negative 5x squared and the plus 4 term. All right? Actually, they're really only created by the negative 5x squared, but we'll get into that a little bit more later. But nice quartic. Okay. Now, it's really critical before we go on to the last exercise that you understand the connection between the factors of this quartic expression and the zeros of this polynomial, right? And there they are. Because we had a factor of x minus 2, we had a 0 of x equals 2. Because we had a factor of x plus 2, we had a 0 of x equals negative 2. We're going to continue to see this connection between the zeros and the factors as we go through lesson after lesson after lesson in this unit. So it's really critical that you grab hold of it right now and start to understand that idea. All right, pause the video now and write down anything you need to. Okay, let's clear out the text. All right, one last problem. Ooh, look at this one. Consider the quartic whose equation is y equals x to the fourth plus 3x cubed minus 35x squared minus 39x plus 70. Whoa! Letter A says, sketch a graph of the quartic on the axes below, label its x-intercepts. So take a moment and use your calculator. All right, with this window, negative 10 to 10 in the x, negative 500 to 500 in the y. That's a huge y window, but you'll need it. Use that window to sketch a graph of that quartic. It will not be symmetric across the y-axis this time. And then either examine the x-axis closely or use the 0 command to figure out what the x-intercepts are. They're all integers, so none of them are obnoxious numbers. So why don't you go ahead and do that? Take your time. All right, so you should have a graph that looks something like this. This is a terrible representation of it, but kind of looks like that. Again, ends pointing in the same direction. This 0 is at negative 7. This 0, not drawn to scale, is at negative 2. This 0 is at 1. And this 0 is at 5. Again, my apologies for the messy graph. All right. Now, letter B says, based on your graph from part A, write the expression in its factored form. So in other words, somehow we can use that graph along with the zeros to know how that quartic factors. Some math teachers will call this graphical factoring, using a graph to help us factor. So I'd like you to think about that a little bit. All right, well, let's talk about it. Now, I want to make you understand how this all works. Okay. Essentially, by drawing that graph in letter A and finding those zeros, we solved this. And what did we have? We had these 4 solutions. All right. But that means that we must have a factor of x plus 7. Right? That's the way the zero product law works. If we have a 0 of x equals negative 7, we had to have a factor of x plus 7. If we have a 0 of negative 2, we have to have a factor of x plus 2. If we have a 0 of 1, we have to have a factor of x minus 1. And if we have a 0 of 5, we have to have a factor of x minus 5. So this is the factored form of this quartic. Isn't that kind of cool? Graphical factoring, using the zeros of a polynomial to figure out the factors of the polynomial. Normally it's the other way around. We use the factors to find the zeros. Here, we use the zeros to find the factors. Pause the video now and think about this a little bit. All right, let's clear out the text and wrap up this lesson. So in the lesson today, what we did is we reviewed the idea of a polynomial being really just a sum of a bunch of power functions where all the powers are positive integers. And then what we did is we looked at how the zeros of those polynomials related to the factors of the polynomials, and we also reviewed the idea of the end behavior being dictated by the highest powered term. All right, you'll get a lot more practice with that on the homework and in the next lesson. For now, I'd like to just thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.